Continuando, então, nossas apresentações desta tarde. Continuing this presentation on this afternoon, I'd like to introduce Dr. Danilo Cardim. Right now, he's in the United States, and he's going to talk about non-invasive assessment of intracranial pressure, principle of various techniques. Dr. Danilo, please, we are eager to hear your talk. Thank you.
Thank you very much, Dr. Columbari, for the invitation to speak at this fabulous symposium. So today, my talk is going to be about some of non-invasive methods to assess intracranial pressure. And also that goes along with my trajectory in studying this topic of non-invasive assessment of intracranial pressure. So to start with, here I have like a table with a summary of basically all the described methods so far in the literature. And these methods can be categorized, just a second here. Just trying to have my pen. So these methods can be categorized in basically 5 different categories. So we have the audiological methods that use, for example, structures in the inner ear to assess intracranial pressure non-invasively. We have ophthalmic methods that have this crosstalk between the brain and the eye. So we have like several described techniques. For example, we have the optic nerve sheath diameter as one of the most described techniques in the literature. And then we also have methods that are based in ultrasonography, mostly relying in transcranial Doppler ultrasonography. My previous colleagues have already talked about some of these methods, but I'll stress it again here. So these methods mostly rely on indices that are extracted from the cerebral blood flow velocity waveform that is obtained with transcranial Doppler ultrasonography. Other methods rely mostly on only the arterial blood pressure waveform by correlating, for example, different features of the arterial blood pressure waveform through mathematical modeling to intracranial pressure. And also, there's methods correlating, for example, the arterial blood pressure to the cerebral blood flow velocity transmission, mostly by using, for example, advanced mathematical techniques such as like data mining and neural networks. And lastly, we have here what Professor Mascarenhas has created, which is the method based on skull bone deformation or expansion of the skull. And also we can subcategorize these different categories of non-invasive ICP methods in methods that provide absolute intracranial pressure values. There is, for example, methods that provide intrinsic calibration of the method in millimeters of mercury or any other pressure unit. We have methods that, for example, do not require calibration. And then we have methods that provide or do not provide continuous measurement of intracranial pressure. So my trajectory into the study of non-invasive intracranial pressure started with Professor Mascarenhas back in, I would say, 2007. So here we take a trip to down on memory lane, where I had this afternoon fun with Professor Mascarenhas, where I was at his house in São Carlos, assessing his intracranial pressure non-invasively with the brain for care sensor. And here we were, back in the days, we were still prototyping this technology. So as we can see here, we had like a very old box, like a blocky device that served as our signal capture platform that was connected to a laptop where we could see different signals and different extractions that we performed for data analysis. And then, but my my work with Professor Mascarenhas started back in the days when we were still doing experimental study in animals. So I was heavily involved during my master's degree to studies that compare primarily the minimally invasive non-invasive intracranial pressure sensor that back in the day it was basically as we can see here, a strain gauge, like extensometer sensor, like glued to the cranial bones. And then we would observe the expansion of the skull due to variations in intracranial pressure, concurrently compared with the traditional intraparenchymal invasive intracranial pressure. So here, for example, it's one of the seminal works that Professor Mascarenhas developed back in the day that compared intracranial pressure measured invasively, minimally invasively with this strain gauge sensor glued to the skull. And then here we perform a series of saline infusion into the subarachnoid space in these rats so as to cause a sudden increase and sustained increases in intracranial pressure over time. So here, as we can see, the first plot represents the traditional invasive intracranial pressure, and the second plot, the minimally invasive intracranial pressure. And we observe that both methods have an agreement of almost 100% most of the time. So this work have led to, for example, the development of the totally non-invasive technique as we have now, that is produced by Bring for Care. But back in the day, we started these experiments not having the complete notion of what would be useful. By that time, we were mostly interested whether we could, for example, observe whether increases in ICP or minimally invasive ICP were correlated. So here, for example, it's a screen that we had when we were doing these infusion tests in these rats. And then here we have the overall trajectory of the minimally invasive ICP over time. So we do see an increase over time along across the infusions. And then here, zoomed out, we have the morphology, the waveform of both signals. So in red, we have the invasive intracranial pressure measured with the intraparenchymal probe. And in green, we have the minimal invasive sensor, the strain gauge. So as we see here, for example, in rats, we do have a little bit of difference concerning the waveforms. So for example, here we do see these periodic larger oscillations that represent the respiratory rate of the rats. But inside this larger oscillatory rate, we see small peaks that correspond itself to the intracranial pressure waveform. So back in those days, we had early findings that even the minimally invasive sensor was able to capture these small oscillations that corresponded to the intracranial pressure waveform that nowadays the totally non-invasive methods relies on for the analysis of the different waveform peaks and different analysis concerning parameters in the brain. And then after working with Professor Mascarenhas during my undergrad years at Federal University of San Carlos and also during my master's degree, I moved on to Cambridge, England, where Professor Marek Czosnika, our previous speaker, was my PhD supervisor. And during my PhD, I had the opportunity to work with different methods to assess intracranial pressure non-invasively. And one of them being the model-based transcranial Doppler ultrasonography method. So basically, how do we use the Doppler principle in sonography, and how does it apply to assessing intracranial pressure non-invasively? So basically here in this representation, we have we have the representation of an artery with the blood flow inside. And then here we have the ultrasound probe that emit basically ultrasound mechanical waves to the brain artery. That here is represented as the middle cerebral artery, which is one of the main focus arteries to assess cerebral blood flow velocity with transcranial Doppler. And then basically, we use these ultrasound signals that are emitted with 2 megahertz ultrasound probes. So the mechanism by which it works is that the signal is reflected when it reaches the vessel by reaching the red blood cells, and then the signal is scattered back to the probe with a frequency shift. So for example, here we see that the probe is emitting a frequency of 2 megahertz, and then the signal is scattering back to the probe with a delay, a shift in frequency. So this shift is correlated, is associated with the velocity of the blood, and that's how we have a surrogate of cerebral blood flow measured by this technique, the transcranial Doppler ultrasonography. And then from the transcranial Doppler signal, we can obtain the cerebral blood flow velocity waveform that is basically mimics the arterial blood pressure systolic and diastolic peaks, from which we can obtain certain markers of cerebrovascular resistance in the brain. For example, described by the Gosling's pulsatility index, that is basically a ratio between the difference of the systolic and diastolic peaks divided by the mean flow velocity in the brain. And also we have another index described as the Power-Solo resistance index, that is basically the same difference systolic minus diastolic divided by the systolic peak instead. So these indices give us, for example, certain markers of the waveform that can later be applied in different model-based non-invasive ICP methods that I will speak now. So to start with, during my PhD, I had the opportunity to work with several methods, and the first one is based on a so-called black box system. So black box system is basically a method that utilizes a transfer function that tries to elucidate inputs and outputs. For example, here we have the input to the black box system is the arterial blood pressure. And then the output system is the cerebral blood flow velocity using transcranial Doppler ultrasonography. So with transcranial Doppler ultrasonography, we have certain characteristics that we can obtain from the waveform. From, say, for example, we have the pulsatility index, we have the diastolic and systolic components. We have, for example, indices of resistance that can be applied to the model, by which we insert certain modification characteristics, and from the input arterial blood pressure measurement, alongside with the cerebral blood flow velocity, we can obtain a non-invasive intracranial pressure that provides us with a non-invasive intracranial pressure waveform. So this method was developed by one of our colleagues, Bernd Schmidt from Germany. And then the second method that I had the opportunity to work with is a model. It's a model that was developed by Professor Chosnik himself. So this method relied mostly on linear regressions between patients that had invasive intracranial pressure measurements alongside with transcranial Doppler measurements. And then what we observed is that there was a function that described this relationship with the arterial blood pressure and the ratio between markers in the cerebral blood flow velocity waveform. So the ratio here that best described the relationship with ICP was the ratio between the diastolic and the mean flow velocity. So initially, this method was developed to assess the non-invasive cerebral perfusion pressure, CPP. But as we know, ICP itself is the difference between the mean arterial blood pressure and the cerebral perfusion pressure that we can obtain non-invasively. Therefore, we can also obtain the invasive intracranial pressure. The third method is a method based on a concept that's also derived from transcranial Doppler ultrasonography, that is so-called critical closing pressure, CRCP. So critical closing pressure, in simple words, is basically the lower threshold of the mean arterial blood pressure that it still allows blood flow to circulate in the brain. So below this threshold, the brain vasculature would collapse and no flow would cease. No flow would circulate in the brain. So there would be a cerebral blood flow cessation in the brain. So we can also use this method to extract the non-invasive cerebral perfusion pressure that is also modeled based on traumatic brain injury patients that had arterial blood pressure, cerebral blood flow velocity with TCD, and intracranial pressure collected. And finally, the fourth method is basically on what is so-called the pulsatility index, which is one of the simplest ways to assess the waveform of transcranial Doppler cerebral blood flow velocity. And with that, we can obtain basically a linear regression when we have an extensive database of traumatic brain injury patients. And for that purpose, one of our colleagues, Kara Budhowski, back when he was a PhD student in the lab, he extracted this formula based on about 300 patients that we had with concurrent measurements of cerebral blood flow velocity, intracranial pressure, and arterial blood pressure. And then we obtained this formula that could be used to assess intracranial pressure non-invasively and also provide us with an absolute value. And then, so this is one of the main papers of my PhD during my time in the lab, in the burn physics lab in Cambridge. So for this study, we collected about 40 prospective TBI patients that were being treated in the neuroscience critical care unit in Edinburgh Hospital. And we basically utilize those collected signals, arterial blood pressure, ICP, and cerebral blood flow velocity with TCD to apply in these 4 different methods that I just talked about. And then we observed the correlation between the absolute measures provided by these non-invasive methods with the real intracranial pressure measured non-invasively. So for these methods, we do see that they present a moderate correlation concerning main values of intracranial pressure, absolute values, with some of them being better than the others. For example, we have here that the black box model based on the transfer function was one of the best in providing these absolute values. But this dramatically changed when we not only rely on the absolute value, but we also rely on the dynamic changes that we observed over time when we monitor a traumatic brain injury patient. So as we know, intracranial pressure is a dynamic physiological signal that changes over time and changes according to the condition of the patient. So for example, here we have a series of examples where on the of the intracranial pressure measured invasively, and the 4 plots below are the non-invasive methods. So as we see, all of these methods, they can replicate these changes in ICP over time that do not necessarily correlate with the absolute mean value. So here we are trying to, for example, differentiate the absolute value to dynamic changes in time. So when we look specifically at dynamic changes in time, these methods are very accurate in replicating these hemodynamic changes in TBI patients. So we have here another example where we see, for example, B waves of intracranial pressure. Here's an example of plateau waves. And also here we have other examples. For example, here we have a succession of 3 different plateau waves, as Professor Charles spoke before. And the non-invasive methods were able to replicate quite confidently these hemodynamic changes over time. So Transcranial Doppler itself is a technique that provides us with a good temporal resolution, although it's limited to the time of monitoring. We cannot nowadays, with the current techniques, have extended monitorings, for example, as we have for intracranial pressure, because it's a sensor that is located outside. But with more recent technologies, for example, robotic and automated transcranial Doppler monitoring, this may change in the very near future. So here, for example, we have the Altman plots that provide us with the 95% confidence interval for prediction for all of these methods I talked about. And overall, we can see that they present with plus minus 10 millimeters of mercury of error in the measurement compared to invasive ICP. So for example, to assess the absolute value of ICP, for example, if you want to determine if a patient has indeed intracranial hypertension that is, for example, characterized with intracranial pressure above 20 millimeters of mercury, having an error of about 10 millimeters of mercury is not very attractive to the clinician. So these methods by themselves, they're not quite reliable to assess the absolute values of intracranial pressure, but instead, if you want to identify, for example, hemodynamic events that are associated with intracranial hypertension, for example, B waves, plateau waves, these methods do provide a very reliable alternative. And then the second method that I had the opportunity to work with during my PhD with one of my colleagues is the optic nerve sheath diameter, that is basically this crosstalk between what happens in the brain in terms of pressure and what happens to the eye. So here, for example, we have a MRI of the head, and then we can observe certain structures of the central nervous system. For example, here we have the optic nerve. We can even observe the optic nerve sheath, and then we can even measure with applying softwares that can measure the caliber of the nerve, the optic nerve sheath diameter. So itself, the optic nerve sheath diameter, ONSED, is a method that takes advantage of these brain-eye crosstalk. And this method, has, because of its practicality, has emerged as one of the most utilized methods in comparison to more complex methods, for example, as transcranial Doppler monitoring and assessment of the waveform. And then, so this method is only possible because there is this, as I said before, this brain-eye crosstalk as means for the non-invasive ICP assessment that is basically relies on the anatomical continuation of the subarachnoid space from the intracranial to the extracranial extension, extracranial compartments of this central nervous system. But we will see this in more details in the next slide. So here, for example, in this figure, this figure represents fluid circulation, where we can observe that the optic nerve located extracranially is surrounded by the subarachnoid space, here represented in blue. And the cerebrospinal fluid circulates freely, and because the intraorbital part of the subarachnoid space is distensible, it can dilate, it can expand when the internal pressure of the cranium expands. So this will be reflected as, a dilation of the optic nerve sheath diameter. So that's why we can utilize certain anatomical features, for example, the diameter of the optic nerve, to correlate with intracranial pressure values, because we can see then when there is increases in pressure, this is translated into increases in diameter of the optic nerve sheath. So we can visualize that with several techniques. For example, we can observe that with CT scans. We can observe that with MRI scans. But in neurocritical care, where ultrasound is readily and highly available, we can utilize ultrasonography to image the optic nerve sheath and also measure the diameter using the calipers that are already inbuilt in the imaging processing software in the ultrasound machine. So here we have, for example, I studied that one of my colleagues, Dr. Kara Roba, published a few years ago. It's a meta-analysis concerning the different assessments of optic sheath diameter as a non-invasive way to assess intracranial pressure. So in the literature, we do observe that the reliability of this method varies quite a lot. So for example, here we have area under the curve values for detection of intracranial hypertension, that is ICP above 20 millimeters of mercury. And as we can see, we have either like very high area under the curves of 0.9 and low area under the curves as 0.74. So in her meta-analysis that compiled all of these studies, we do see that the overall area under the hierarchical summary received operating characteristic curve, the RAP curve, was very high of 0.924, which demonstrates the reliability of this method, at least to identify events of intracranial hypertension. And also, back in the days during our PhD times, we did a prospective study in Cambridge where we had about 100 patients that that had measurements of optic nerve sheath for about like 400 times. So we collected about 4 measurements of optic nerve sheath diameter along the days patients were in the unit, yielding this large assessment of more than 400 measurements of optic nerve sheath diameter and invasive intracranial pressure. And we observed that these 2 measurements, they were highly correlated with a very high ability to detect events of intracranial hypertension with a area under the curve of 0.9. And also we found that the best threshold to identify events of intracranial hypertension characterized as 20 millimeters of mercury was 5.8 millimeters of optic nerve sheath diameter. And also for this work, we were able to create a linear regression between these measurements that we had that provided us with a linear regression model that can be utilized to measure non-invasive ICP based on optic nerve sheath diameter in millimeters of mercury. And then also we had the opportunity during this time to perform a pilot study in pediatric patients that had concurrent measurement of invasive intracranial pressure and optic nerve sheath diameter. And with this pediatric population, we also observed a very high correlation between these 2 measurements. And the only difference here is that the identification of intracranial hypertension is given by a lower threshold due to the anatomical differences between adult patients and pediatric patients. So as take-home messages for studies that explored intracranial pressure measured non-invasively, as we know so far from the literature, the estimation of ICP absolute values, in millimeters of mercury or any pressure unit, is limited at the current state of development for all of the non-invasive ICP methods. None of them are 100% reliable in providing absolute values. All of them have advantages and limitations in this concern, but overall, none of them can be accurately utilized to provide the clinician with absolute values of ICP. And specifically for model-based methods, for example, that rely on waveform analysis, say, for example, transcranial Doppler velocity, the inaccuracy of the methods in providing these absolute measures of pressure suggested to be associated with the matter of non-specific, non-invasive ICP calibrations. Because, for example, when you try to establish a model of cerebral blood flow circulation that will produce a non-invasive ICP method, you need to rely on certain population cohorts. And as we know, traumatic brain injury is a very heterogeneous population and disease itself. So one of the main difficulties in using these data is to normalize to a single population value because of this huge heterogeneity. But overall, as we know also from the literature, is that the non-invasive monitoring methods can be used to screen patients, for example, for identification of intracranial hypertension, or for example, as the Brain for Care method provides to detect impairments of intracranial compliance in situations where really the invasive interventions cannot be promptly accessed, or for example, it's even forbidden in certain clinical situations. So additionally, non-invasive screening can be done in patients where there's relatively low suspicion of elevated SCP, but the possibility needs to be ruled out. So for example, in emergency rooms, for example, after traumatic brain injury, and other pathologies. And for example, this may decrease the placement of invasive sensors in patients who, in retrospect, did not actually need invasive ICP monitor, or even need immediate invasive ICP monitoring for clinical management. So with that, I would like to thank you everybody for organizing this fantastic symposium. And overall, thank you, Professor Sérgio, for everything you did for my life. You were a transforming agent in my life, and to this day, you're still my inspiration. So thank you very much.
Thank you, Dr. Danilo. Very nice talk.